Hello, everyone, and welcome to my project presentation for combined gas cycle using Aspen simulation for ME210 Advanced Thermodynamics. My name is JLCSia, and I'll be detailing here the steps that I did in Aspen simulation and some of the things that I went through in order to make this simulation happen. To start off, I'm going to discuss the table of contents of this presentation, which are a brief description of the combined gas cycle, and then a step-by-step procedure on how I conducted the entire simulation, and then followed by the results of the simulation, where I'm going to put in some of my insight as to how it was obtained, and finally, some concluding statements about the entire simulation. So we're going to start with a brief description of the cycle itself. So the combined gas cycle is the combination of a gas turbine and a steam turbine through the means of a heat exchanger. This heat exchanger takes some of the heat from the exhausted gas turbine and transfers it to water. This water is then turned to steam, which is then used to drive a steam turbine. So you basically have two turbines running, and for the price of this added generation, you simply recovered heat that was exhausted by the gas turbine. So on this slide here, this shows the entire Aspen plus version 11 simulation. So this is the completed combined gas cycle, complete with material streams and model streams. And this is what we're going to be discussing as we go on through the presentation. So what makes the combined gas cycle possible? So gas turbines, as per their natural state of operation, they have high operating temperatures. Now, even if your gas turbine can push out 200, 300 megawatts of power, it's still exhausting a relatively hot amount of gas. So for our case, this gas still packs a ton of heat. Now, why is a steam turbine the partner for a gas turbine? That is because a steam turbine has a very flexible operational parameter in comparison with a gas turbine. So as someone who works from a geothermal power plant, our power plant works at 350 degrees and zero point 0.5 megapascal, so basically saturated steam. What makes this combination so great is that as long as the gas turbine keeps on generating electricity, it's going to keep on rejecting a ton of heat. By using a heat exchanger to absorb this heat, we can transfer this to water, which then turns into steam and generate a few extra megawatts of electricity for the power plant. So now we're going to proceed to the step-by-step procedure on how we conduct the simulation for Aspen Plus version 11. So here's an outline for the entire process that we've conducted. First step is we're going to set up the units and components of the simulation. The second is we're going to set up the gas turbine side of the simulation, followed by the steam turbine side of the simulation. And finally, we're going to consolidate both cycles and refine any other errors or any wrinkles that we may see in the simulation. And finally, we're going to discuss the results and conclusion. So we're going to start with the setup of units and components. So Aspen generally doesn't know what components or what chemicals or what compounds you're even going to use for the simulation. So this is where we put the general idea or the general components or chemicals that we may be using for our simulation. So for this case, we will be putting the typical components or typical chemical components that we'll be seeing in a typical cycle, kind of like water for our steam turbine, methane for the gas turbine. Now, natural gas doesn't generally always have methane, so we're gonna take into account some ethane and propane. There are also other factors to consider like nitrogen and oxygen, which mainly is comprising of air, then some of its products like nitrogen, nitrous oxide, nitric oxide, nitrous dioxide, and even carbon monoxide and carbon dioxide. So we place everything here in the component specification of Aspen simulation. So this component list takes inspiration from the Rankine cycle tutorial that adds three hydrocarbons that is typically found in natural gas. So different compounds of nitrogen and carbon dioxide is included as well. After we've set up the components that we think we're going to use for the simulation, we're going to define how Aspen is going to tackle these components. In a way, we're going to tell Aspen how it's going to calculate or where it's going to base its calculations when conducting the simulation. So for our case, our property methods and options is going to be based on the Pengrove simulation, since we're going to be using a gas turbine. So with everything set up, we can now go to the simulation tab on the bottom left of the screen. The next phase would be to set up the gas turbine side of the simulation. So in order to create a gas turbine cycle, we first have to define some of the more obvious parts of the gas turbine. So we expect our gas turbine to at least produce 200 megawatts of electricity. And we also expect it to have an operating temperature or a temperature high of 1250 degrees Celsius from that output of 200 megawatts. Our fuel gas, it will be at 15 degrees and 15 and 21 bar. Air is going to be at 20 degrees and 1 bar. The combined gas flow rate would be at 210 kilograms per second, and our combustion temperature, which is equal to the temperature high, would be at 1250 degrees Celsius. The combustor that we'll be using for the simulation would be modeled using the R-Gibbs reactor. So to set up the gas turbine, we're going to put some models onto our simulation tab. So some of the models that we've used is that air compressor and a letdown valve, a R-Gibbs combustion from the reactors tab on our model palette, and another compressor, but this time it's flipped and it's for the turbine. Some of the material streams that we're going to be using would be for the fuel gas, which is the supply side of the letdown valve, the low pressure gas, which is the discharge of the letdown valve, air number 1, which is the supply for air compressor, air 2 would be the pressurized air, combined gas is the gas that is combusted by the combustor, and finally gas turbine exit 1, which is the discharge for our gas turbine. Afterwards, we're going to set the individual parameters for each model and stream. For our air compressor, it's going to be an isentropic type. It has a discharge pressure of 15 bar G, an isentropic and mechanical efficiency of 0.85. Our air, or the intake air, would be at a flash type temperature and pressure. Temperature would be at 20 degrees Celsius. Pressure would be at 1.01 bar. Our flow basis would be based on mass at 110 kilograms per second, and our composition would be based on mass flow at kilograms per second, where our N2 would be at 191 or 191.97 kilograms per second, and our oxygen at 51.03 kilograms per second. The letdown valve would be at default, which is the adiabatic flash for specified outlet pressure, and an outlet pressure of 21 bar. Our fuel gas will be a flash type temperature and pressure. It will have a temperature of 15 degrees Celsius, a pressure of 21 bar, a total flow basis using mass, which would be at 100 kilograms per second, a composition of mole flow at kilomoles per hour, being 1 kilomole per hour of C1 or methane for our mole flow. Our R-Gibbs combustor will have the default calculate phase equilibrium and chemical equilibrium with a pressure of 8 bar and a temperature of 1250 degrees. Our gas turbine would be a model and type turbine, and it will be an isentropic type with an expected power produced of 200 megawatts, with an isentropic efficiency of 0.88 and a mechanical efficiency of 0.85. So to make our calculations faster and easier, we can include a calculator that automatically changes the pressure of the fuel when the air pressure changes. This makes it easier for us when we're conducting the simulation so that we won't be so overwhelmed by the amount of changes that we have to do into the system. In a way, we automate the simulation part of the system. So first, we have to set our variable of P fuel and P air. P fuel will be of the streams category, and the stream in question would be the LP gas. The variable in question is pressure, and the units used would be bar. It is important to indicate that it is an import variable. The second would be P air. P air is a block, and by block, we are referring to the air compressor, with the variable in question being pressure and units at bar. It's also important to indicate it should be an export variable. Finally, at the Calculate tab, we're going to enter the formula that we're going to use for the automation of our simulation. For this case, P air would be equal to P fuel. Now that we've completed it, we can run the first portion of our simulation. So by running our gas turbine cycle, we're going to get this portion of the slide. So in general, the parameters that we've entered would be displayed by Aspen Plus here. And by analyzing this, or even by seeing this slide, we can see that our air that is exiting our gas turbine is at 890 degrees Celsius. Now, this 890 degrees Celsius still packs a ton of heat. And by using this combined gas cycle, we're going to get as much heat from that exhaust gas and transfer it to the steam turbine. So some of the initial gas turbine results that we've calculated would be we have a total power produced of 200 megawatts. We've added heat into the system at an amount of 358 megawatts, which is heat added by the combustor. Our compressor would be needing work at 62 megawatts. Now we're going to create the setup for the steam turbine side of the simulation. Now to set up the steam turbine portion, we've already completed the compositions and even some of the needed chemicals for our simulation. So we're just going to piggyback off of that, off of our gas turbine simulation. So to set up for our steam turbine portion, we're going to use the following models. A heat exchanger, which is a multiple exchanger found on the model palette on Aspen Plus. We're going to require another compressor, in this case, which is our turbine, a heater from the exchangers portion of the model palette, which will act as our condenser, and finally a pump. We now set the individual parameters for each model and stream. For our heat exchanger, our model fidelity is going to be shortcut. This is going to make our calculations and our simulation a little bit faster and easier for us. The hot fluid should be at the tube. The flow of the direction should be countercurrent. Now, for our exchanger specification, we have to put cold stream outlet temperature increase. We use this because we expect a change in phase for our cold fluid. So for this case, we expect that our cold water would change in phase into vapor. And the value of temperature increase would be at 260 degrees Celsius with a minimum temperature approach of 1 degree Celsius. To set up our steam turbine, our model is going to be turbine. The type is isentropic with a discharge pressure of 10 kilopascals. Our isentropic efficiency would be at 0.88 and a mechanical efficiency of 0.85. Now, to further refine our results for the steam turbine, we have to first define the parameters that our steam turbine would be taking into account. So, as we see the steam turbine block, we're gonna go to the convergence tab. On the convergence tab, we're gonna specify that the valid phase is vapor liquid free water. This is important because if we input the wrong valid phases, it's going to create errors in our Aspen simulation. Afterwards, we're going to go to the block options found on the steam turbine block on the left side of Aspen simulation. We need to do this because Aspen is going to calculate our steam turbine formulas and calculations using the Pengrove methods. So if we want accurate results for our steam turbine, we're going to need a property method of steam TA, which takes into account that Aspen is going to use steam TA property methods in order to calculate a more accurate result. Our condenser would be a flash type pressure and vapor fraction. We use vapor fraction because we want the condenser to eject as much saturated liquid as possible at a pressure of 10 kilopascals. We also put here as well that the valid phases would be vapor, liquid, free water. We're also going to set up our high pressure water stream, the flash type would being pressure and vapor fraction, where the pressure being 5 bar and our vapor fraction being 0 to indicate that it is liquid. Our flow basis would be based on mass at 125 kilograms per second. The composition of the entire stream would be water, and it's going to be based on the mass fractions of H2O being a value of 1. Our pump, on the other hand, would simply have a discharge pressure of 5 bar and an efficiency for the pump of 0.98 and a driver efficiency of 0.95. So on this slide, we see the completed steam turbine simulation. Now, we haven't let Aspen run the simulation yet because our heat exchanger still doesn't know what our gas turbine exhaust 1 or what the properties of gas turbine exhaust 1 is. So we're going to define that as we consolidate both cycles. So now we're going to consolidate both the gas turbine, the steam turbine, and make them into one. Now consolidating both the gas turbine and the steam turbine is one of the major obstacles faced during the project. This is because we're supposed to strike a balance between the amount of mass flowing out of gas turbine exhaust 1 as well as the amount of water that we're going to put inside the heat exchanger. We also have to make sure that the exit of the heat exchanger for our cold side, which is the water, is a is an achievable temperature for the heat exchanger. Sometimes when we input different calculations into the simulation, we would get a negative result for our temperatures. So we have to correct and refine our calculations for the simulation. So for our case, and to set up the consolidation, we're gonna put the gas turbine exhaust 1 as the inlet for the heat exchanger. Afterwards, we're going to create another material stream, which is the exit or the discharge of the heat exchanger for the hot side. Finally, we're going to connect the high pressure water stream to the cold inlet of the heat exchanger, and we're going to create another stream named high pressure steam, as this is the outlet for the heat exchanger. With all our inputs done, we can now run the simulation. So with our steam and gas turbine portions of the simulation connected, we can now then run the simulation and create the desired combined gas power plant. So on this slide, this shows the completed combined gas power cycle that we've completed on Aspen simulation. Our heat exchanger serves as the joint or the connection between the gas turbine and the steam turbine. Our gas turbine is exhausting 890 degrees Celsius. And we're going to use that 890 degrees Celsius onto our heat exchanger to heat our high pressure water at 45 degrees to 305 degrees Celsius at 5 bars. So this is going to give us the steam that we need in order to power our steam turbine. So here are the summary of our results from our simulation. Our steam turbine produces 66 megawatts of electricity. Our condenser rejects heat at the quantifiable amount of 283 megawatts. Our pump work requires about 66 kilowatts or 0.66 megawatts. And finally, we're going to discuss the results for our Aspen simulation. So now we are on to the results and conclusion of the outline. So for the gas turbine, our power produced is 200 megawatts. The heat added by the combustor is at 358 megawatts. Our compressor work is at 62 megawatts. Our net work, which is the turbine work deducted by the compressor work, is at 137 megawatts. The cycle efficiency of the gas turbine cycle alone is at 38.47%, and we have a back work ratio of 1.27, which is the quotient between the temperature differences of the compressor and the turbine. Our power produced for the steam turbine is 66 megawatts, heat rejected by the condenser is 283 megawatts, and our pump work, as we've said earlier, is at 66 kilowatts or 0.66 megawatts. Our network is at 65.9 megawatts, and we have a cycle efficiency of 18.29%. To summarize our results for the combined gas cycle, we have a total network of about 203.93 megawatts, which is the gas turbine network plus the steam turbine network. Our cycle efficiency is at 56.87%, and our auxiliary work is at 62.1 megawatts, which is the work done by our compressor and pump. We also have here some of the data that we've extracted from Aspen. This is located from the results section, and this is taken from the material streams for our simulation. We can see here that our gas turbine exhaust gas is at 890 degrees Celsius, and it exits the heat exchanger at 189.57 degrees Celsius. Our high pressure steam achieves our desired temperature, which is at 305 degrees Celsius. On the right side, we also have the energy flows. The heat exchanger duty, the combustor duty, and the condenser duty were all mentioned in the previous slides. But some notable additions into this simulation is that our high heating valve for our fuel is at 6,106,665 kilowatts, and we also have a lower heating value for our fuel, which is at 5,503,304,000 kilowatts. We also detail or summarize our equipment efficiencies for the entire cycle. As we said before, air compressor, isentropic and mechanical efficiency of it is at 0.85. Condensate pump, the isentropic is at 0.98 and its mechanical is 0.95. And for a gas and steam turbine, they both have an isentropic efficiency of 0.88 and a mechanical efficiency of 0.85. And finally, we come to the conclusion of my project, which is the concluding statements of the simulation. Combined gas cycle has a high power output. Stating the obvious, a combined gas cycle utilizes a gas turbine and a steam turbine. What makes this cycle so attractive to a lot of investors and even engineers, or even engineering, procurement, and construction services, is that a combined gas cycle gives you more for what you put inside it. So a gas turbine can only give you so much power, but it's still exhausting a lot of heat. And that heat, by recovering that heat, you can use it on a steam turbine to further your efficiency for your plant. Which brings us to the second concluding statement, which is the high cycle efficiency. Our cycle efficiency was at 56%. Now, this high cycle efficiency is such an advantage for different manufacturers, different plants, because this means that we can extract 50% of the heat added into the system, and we can turn that 50% into usable work. Now, a combined gas power plant can be considered a simplified power plant. We say this because if you construct a gas turbine power plant and construct an independent steam turbine power plant, you're going to be facing different challenges here because a steam power plant must require a boiler. Now, this boiler is one of the factors as to why a steam power plant would have such a high and very expensive operating cost because a boiler needs to be kept at its rated temperature. If you were to shut down that boiler, you're going to be expending a lot of heat just to keep it back to its nominal operating temperature. By utilizing a combined gas power plant cycle, you remove that boiler from the equation by using the wasted heat from the gas turbine. So you don't really have to add additional equipment into your power plant in order to receive a bigger energy output. You're, what you're doing here is that you're simply taking exhaust heat or wasted heat from the gas turbine and transferring it to the steam turbine to produce more electricity. And finally, phased installation. Now, this might not be so important during the operation of the combined gas power plant itself, but for different petrochemical companies, for different EPCs or engineering procurement and construction companies, having a phased installation for your power plant can be an advantage. This is because gas turbines can be installed sooner and faster than a steam power plant. So when you're constructing your refinery, you can put it a gas turbine to supply power to all your auxiliaries and all your equipment. And then when you've completed everything, you can also build a steam power plant in conjunction with other construction projects for your refinery. So this means that you can anticipate that as you complete your plant, you can also garner additional power from your gas turbine by using its wasted heat and transferring it into the steam turbine. And that concludes my presentation for my project, the combined gas power cycle. Thank you, everyone.